1926 Subpart V Appendix E, Protection from Flames and Electric Arcs. Appendix E to Subpart V of Part 1926, Protection from Flames and Electric Arcs. I. Introduction. Paragraph G of Section 1926.960 addresses protecting employees from flames and electric arcs. This paragraph requires employers to 1. Assess the workplace for flame and electric arc hazards. Paragraph G. 1. 2. Estimate the available heat energy from electric arcs to which employees would be exposed. Paragraph G. 2. 3. Ensure that employees wear clothing that will not melt or ignite and continue to burn when exposed to flames or the estimated heat energy. Paragraph G. 3. And 4. Ensure that employees wear flame-resistant clothing and protective clothing and other protective equipment that has an arc rating greater than or equal to the available heat energy under certain conditions. Paragraphs G. 4 and G. 5. This appendix contains information to help employers estimate available heat energy as required by Section 1926.960 G. 2. Select protective clothing and other protective equipment with an arc rating suitable for the available heat energy as required by Section 1926.960 G. 5. And ensure that employees do not wear flammable clothing that could lead to burn injury as addressed by Sections 1926.960 G. 3 and G. 4. 2. Assessing the workplace for flame and electric arc hazards. Paragraph G. 1 of Section 1926.960 requires the employer to assess the workplace to identify employees exposed to hazards from flames or from electric arcs. This provision ensures that the employer evaluates employee exposure to flames and electric arcs so that employees who face such exposures receive the required protection. The employer must conduct an assessment for each employee who performs work on or near exposed, energized parts of electric circuits. A. Assessment Guidelines. Sources: electric arcs. Consider possible sources of electric arcs, including energized circuit parts not guarded or insulated, switching devices that produce electric arcs in normal operation, sliding parts that could fault during operation, for example, rack-mounted circuit breakers, and energized electric equipment that could fail, for example, electric equipment with damaged insulation or with evidence of arcing or overheating. Exposure to flames. Identify employees exposed to hazards from flames. Factors to consider include the proximity of employees to open flames, and for flammable material in the work area, whether there is a reasonable likelihood that an electric arc or an open flame can ignite the material. Probability that an electric arc will occur. Identify employees exposed to electric arc hazards. The Occupational Safety and Health Administration will consider an employee exposed to electric arc hazards if there is a reasonable likelihood that an electric arc will occur in the employee's work area. In other words, if the probability of such an event is higher than it is for the normal operation of enclosed equipment. Factors to consider include, for energized circuit parts not guarded or insulated, whether conductive objects can come too close to or fall onto the energized parts. For exposed, energized circuit parts, whether the employee is closer to the part than the minimum approach distance established by the employer, as permitted by Section 1926.960 C. 1, 3. Whether the operation of electric equipment with sliding parts that could fault during operation is part of the normal operation of the equipment or occurs during servicing or maintenance, and for energized electric equipment, whether there is evidence of impending failure, such as evidence of arcing or overheating. Table 1 provides task-based examples of exposure assessments. The employee is not exposed to flame or electric arc hazard under normal operation of enclosed equipment, such as closing or opening a switch. When the employer properly installs and maintains enclosed equipment, and there is no evidence of impending failure. The employee is exposed to flame or electric arc hazard under normal operation of enclosed equipment, such as closing or opening a switch. When there is evidence of arcing or overheating. The employee is exposed to flame or electric arc hazard under normal operation of enclosed equipment, such as closing or opening a switch. When parts of the equipment are loose or sticking, or the equipment otherwise exhibits signs of lack of maintenance. The employee is exposed to flame or electric arc hazard when servicing electric equipment, such as racking in a circuit breaker or replacing a switch. The employee is not exposed to flame or electric arc hazard when inspection of electric equipment with exposed energized parts. When the employee is not holding conductive objects and remains outside the minimum approach distance established by the employer. The employee is exposed to flame or electric arc hazard when inspection of electric equipment with exposed energized parts. When the employee is holding a conductive object, such as a flashlight, that could fall or otherwise contact energized parts, irrespective of whether the employee maintains the minimum approach distance. The employee is exposed to flame or electric arc hazard when inspection of electric equipment with exposed energized parts. When the employee is closer than the minimum approach distance established by the employer, for example, when wearing rubber insulating gloves or rubber insulating gloves and sleeves. The employee is exposed to flame or electric arc hazard when using open flames, for example, in wiping cable splice sleeves. 3. Protection against burn injury. A. Estimating available heat energy. Calculation methods. Paragraph G2 of Section 1926.960 provides that, for each employee exposed to an electric arc hazard, the employer must make a reasonable estimate of the heat energy to which the employee would be exposed if an arc occurs. Table 2 lists various methods of calculating values of available heat energy from an electric circuit. The Occupational Safety and Health Administration does not endorse any of these specific methods. Each method requires the input of various parameters, such as fault current, the expected length of the electric arc, the distance from the arc to the employee, and the clearing time for the fault, that is, the time the circuit protective devices take to open the circuit and clear the fault. The employer can precisely determine some of these parameters, such as the fault current and the clearing time, for a given system. The employer will need to estimate other parameters, such as the length of the arc and the distance between the arc and the employee, because such parameters vary widely. Table 2. Methods of calculating incident heat energy from an electric arc. 1. Standard for Electrical Safety Requirements for Employee Workplaces, NFPA 70E 2012, Annex D, Sample Calculation of Flash Protection Boundary. 2. Doughty, G.E., Neal, T.E., and Floyd 2, HUL, Predicting Incident Energy to Better Manage the Electric Arc Hazard on 600 V Power Distribution Systems, Record of Conference Papers IEEE's 45th Annual Petroleum and Chemical Industry Conference, September 28 to 30, 1998. 3. Guide for Performing Arc Flash Hazard Calculations, IEEE STD 1584-2002, 1584A 2004, Amendment 1 to IEEE STD 1584-2002, and 1584B 2011, Amendment 2, Changes to Clause 4 of IEEE STD 1584-2002. Asterisk. 4. ARCPRO, a commercially available software program developed by Connectrix, Toronto, on CA. Asterisk. This appendix refers to IEEE STD 1584-2002 with both amendments as IEEE STD 1584B 2011. The amount of heat energy calculated by any of the methods is approximately inversely proportional to the square of the distance between the employee and the arc. In other words, if the employee is very close to the arc, the heat energy is very high, but if the employee is just a few more centimeters away, the heat energy drops substantially. Thus, estimating the distance from the arc to the employee is key to protecting employees. The employer must select a method of estimating incident heat energy that provides a reasonable estimate of incident heat energy for the exposure involved. Table 3 shows which methods provide reasonable estimates for various exposures. Selecting a reasonable incident energy calculation method. Key: 1 phi, single-phase arc in open air. 3 phi A, 3-phase arc in open air. 3 phi B, 3-phase arc in an enclosure, box. Y. Acceptable, produces a reasonable estimate of incident heat energy from this type of electric arc. N. Not acceptable, does not produce a reasonable estimate of incident heat energy from this type of electric arc. Y. C. Acceptable, produces a reasonable, but conservative, estimate of incident heat energy from this type of electric arc. Notes. 1. Although the Occupational Safety and Health Administration will consider these methods reasonable for enforcement purposes when employers use the methods in accordance with this table, employers should be aware that the listed methods do not necessarily result in estimates that will provide full protection from internal faults in transformers and similar equipment or from arcs in underground manholes or vaults. 2. At these voltages, the presumption is that the arc is three-phase unless the employer can demonstrate that only one phase is present or that the spacing of the phases is sufficient to prevent a multi-phase arc from occurring. 3. Although the Occupational Safety and Health Administration will consider this method acceptable for purposes of assessing whether incident energy exceeds 2.0 calories per square centimeter, the results at voltages of more than 15 kilovolts are extremely conservative and unrealistic. 4. The Occupational Safety and Health Administration will deem the results of this method reasonable when the employer adjusts them using the conversion factors for three-phase arcs in open air or in an enclosure, as indicated in the program's instructions. Selecting a reasonable distance from the employee to the arc. In estimating available heat energy, the employer must make some reasonable assumptions about how far the employee will be from the electric arc. Table 4 lists reasonable distances from the employee to the electric arc. The distances in Table 4 are consistent with national consensus standards, such as the Institute of Electrical and Electronic Engineers National Electrical Safety Code, ANSI/IEEE C2-2012, and IEEE Guide for Performing Arc Flash Hazard Calculations, IEEE STD 1584B 2011. The employer is free to use other reasonable distances, but must consider equipment enclosure size and the working distance to the employee in selecting a distance from the employee to the arc. The Occupational Safety and Health Administration will consider a distance reasonable when the employer bases it on equipment size and working distance. Table 4. Selecting a reasonable distance from the employee to the electric arc. Selecting a reasonable arc gap. For a single-phase arc in air, the electric arc will almost always occur when an energized conductor approaches too close to ground. Thus, an employer can determine the arc gap, or arc length, for these exposures by the dielectric strength of air and the voltage on the line. The dielectric strength of air is approximately 10 kilovolts for every 25.4 millimeters, 1 inch. For example, at 50 kilovolts, the arc gap would be 50 divided by 10 by 25.4, or 50 by 2.54, which equals 127 millimeters, 5 inches. For three-phase arcs in open air and in enclosures, the arc gap will generally be dependent on the spacing between parts energized at different electrical potentials. Documents such as IEEE STD 1584B 2011 provide information on these distances. Employers may select a reasonable arc gap from Table 5, or they may select any other reasonable arc gap based on spark over distance or on the spacing between 1. Live parts at different potentials or 2. Live parts and grounded parts, for example, bus or conductor spacings in equipment. In any event, the employer must use an estimate that reasonably resembles the actual exposures faced by the employee. Table 5. Selecting a reasonable arc gap. Making estimates over multiple system areas. The employer need not estimate the heat energy exposure for every job task performed by each employee. Paragraph G2 of Section 1926.960 permits the employer to make broad estimates that cover multiple system areas provided that 1. The employer uses reasonable assumptions about the energy exposure distribution throughout the system, and 2. The estimates represent the maximum exposure for those areas. For example, the employer can use the maximum fault current and clearing time to cover several system areas at once. Incident heat energy for single-phase to ground exposures. Table 6 and Table 7 provide incident heat energy levels for open air, phase to ground electric arc exposures typical for overhead systems. Table 6 presents estimates of available energy for employees using rubber insulating gloves to perform work on overhead systems operating at 4 to 46 kilovolts. The table assumes that the employee will be 380 millimeters, 15 inches, from the electric arc, which is a reasonable estimate for rubber insulating glove work. Table 6 also assumes that the arc length equals the spark over distance for the maximum transient over voltage of each voltage range. 3 To use the table, an employer would use the voltage, maximum fault current, and maximum clearing time for a system area and, using the appropriate voltage range and fault current and clearing time values corresponding to the next higher values listed in the table, select the appropriate heat energy, 4, 5, 8, or 12 calories per square centimeter, from the table. For example, an employer might have a 12,470 volt power line supplying a system area. The power line can supply a maximum fault current of 8 kA with a maximum clearing time of 10 cycles. For rubber glove work, this system falls in the 4.0 to 15.0 kV range. The next higher fault current is 10 kV, the second row in that voltage range, and the clearing time is under 18 cycles, the first column to the right of the fault current column. Thus, the available heat energy for this part of the system will be 4 calories per square centimeter or less from the column heading, and the employer could select protection with a 5 cal/cm2 rating to meet section 1926.960 G5. Alternatively, an employer could select a base incident energy value and ensure that the clearing times for each voltage range and fault current listed in the table do not exceed the corresponding clearing time specified in the table. For example, an employer that provides employees with arc flash protective equipment rated at 8 calories per square centimeter can use the table to determine if any system area exceeds 8 calories per square centimeter by checking the clearing time for the highest fault current for each voltage range and ensuring that the clearing times do not exceed the values specified in the 8 cal/cm2 column in the table. Table 7 presents similar estimates for employees using liveline tools to perform work on overhead systems operating at voltages of 4 to 800 kV. The table assumes that the arc length will be equal to the spark over distance 4 and that the employee will be a distance from the arc equal to the minimum approach distance minus twice the spark over distance. The employer will need to use other methods for estimating available heat energy in situations not addressed by Table 6 or Table 7. The calculation methods listed in Table 2 and the guidance provided in Table 3 will help employers do this. For example, employers can use IEEE STD 1584B 2011 to estimate the available heat energy and to select appropriate protective equipment for many specific conditions, including lower voltage, phase-to-phase arc, and enclosed arc exposures. Table 6. Incident heat energy for various fault currents, clearing times, and voltages of 4.0 to 46.0 kV, rubber insulating glove exposures involving phase-to ground ARCS in open air only. This table is for open air, phase-to-ground electric arc exposures. It is not for phase-to-phase arcs or enclosed arcs, arc in a box. The table assumes that the employee will be 380 mm, 15 inches, from the electric arc. The table also assumes the arc length to be the spark over distance for the maximum transient over voltage of each voltage range. See Appendix B to this subpart. The Occupational Safety and Health Administration calculated the values in this table using the ARCPRO method listed in Table 2. The voltage range is the phase-to-phase system voltage. Table 7. Incident heat energy for various fault currents, clearing times, and voltages, liveline tool exposures involving phase-to ground ARCS in open air only. This table is for open air, phase-to-ground electric arc exposures. It is not for phase-to-phase arcs or enclosed arcs, arc in a box. The table assumes the arc length to be the spark over distance for the maximum phase-to-ground voltage of each voltage range. See Appendix B to this subpart. The table also assumes that the employee will be the minimum approach distance minus twice the arc length from the electric arc. The Occupational Safety and Health Administration calculated the values in this table using the ARCPRO method listed in Table 2. For voltages of more than 72.6 kV, employers may use this table only when the minimum approach distance established under Section 1926.960, C1. Table 7. Incident heat energy for various fault currents, clearing times, and voltages, liveline tool exposures involving phase-to ground arcs in open air only. Table 7. Incident heat energy for various fault currents, clearing times, and voltages, liveline tool exposures involving phase-to ground arcs in open air only. B. Selecting protective clothing and other protective equipment. Paragraph G5 of Section 1926.960 requires employers, in certain situations, to select protective clothing and other protective equipment with an arc rating that is greater than or equal to the incident heat energy estimated under Section 1926.960 G2. Based on laboratory testing required by ASTM F1506-10A, the expectation is that protective clothing with an arc rating equal to the estimated incident heat energy will be capable of preventing second-degree burn injury to an employee exposed to that incident heat energy from an electric arc. Note that actual electric arc exposures may be more or less severe than the estimated value because of factors such as arc movement, arc length, arcing from recloosing of the system, secondary fires or explosions, and weather conditions. Additionally, for arc rating based on the fabric's arc thermal performance value 5, ATPV, a worker exposed to incident energy at the arc rating has a 50% chance of just barely receiving a second-degree burn. Therefore, it is possible, although not likely, that an employee will sustain a second-degree, or worse, burn wearing clothing conforming to Section 1926.960 G5 under certain circumstances. However, reasonable employer estimates and maintaining appropriate minimum approach distances for employees should limit burns to relatively small burns that just barely extend beyond the epidermis, that is, just barely a second-degree burn. Consequently, protective clothing and other protective equipment meeting Section 1926.960 G5 will provide an appropriate degree of protection for an employee exposed to electric arc hazards. Paragraph G5 of Section 1926.960 does not require arc-rated protection for exposures of 2 calories per square centimeter or less. Untreated cotton clothing will reduce a 2 cal/cm2 exposure below the 1.2 to 1.5 cal/cm2 level necessary to cause burn injury, and this material should not ignite at such low heat energy levels. Although Section 1926.960 G5 does not require clothing to have an arc rating when exposures are 2 calories per square centimeter or less, Section 1926.960 G4 requires the outer layer of clothing to be flame resistant under certain conditions, even when the estimated incident heat energy is less than 2 calories per square centimeter, as discussed later in this appendix. Additionally, it is especially important to ensure that employees do not wear undergarments made from fabrics listed in the note to Section 1926.960 G3, even when the outer layer is flame resistant or arc rated. These fabrics can melt or ignite easily when an electric arc occurs. Logos and name tags made from non-flame resistant material can adversely affect the arc rating or the flame resistant characteristics of arc rated or flame resistant clothing. Such logos and name tags may violate Section 1926.960 G3, G4, or G5. Paragraph G5(2) of Section 1926.960 provides that arc-rated protection is not necessary for the employee's feet when the employee is wearing heavy-duty work shoes or boots. Finally, Section 1926.960 G5, 3, G5, 4, and G5 require arc-rated head and face protection as follows in the table. These ranges assume that employees are wearing hard hats meeting the specifications in Section 1910.135 or Section 1926.100 B2 as applicable. The arc rating must be a minimum of 4 calories per square centimeter less than the estimated incident energy. Note that Section 1926.960 G5 permits this type of head and face protection, with a minimum arc rating of 4 calories per square centimeter less than the estimated incident energy, at any incident energy level. Note that Section 1926.960 G5 permits this type of head and face protection at any incident energy level. 4. Protection against ignition. Paragraph G3 of Section 1926.960 prohibits clothing that could melt onto an employee's skin or that could ignite and continue to burn when exposed to flames or to the available heat energy estimated by the employer under Section 1926.960 G2. Meltable fabrics such as acetate, nylon, polyester, and polypropylene, even in blends, must be avoided. When these fibers melt, they can adhere to the skin, thereby transferring heat rapidly, exacerbating burns, and complicating treatment. These outcomes can result even if the meltable fabric is not directly next to the skin. The remainder of this section focuses on the prevention of ignition. Paragraph G5 of Section 1926.960 generally requires protective clothing and other protective equipment with an arc rating greater than or equal to the employer's estimate of available heat energy. As explained earlier in this appendix, untreated cotton is usually acceptable for exposures of 2 calories per square centimeter or less. 0.6 If the exposure is greater than that, the employee generally must wear flame-resistant clothing with a suitable arc rating in accordance with Section 1926.960 G4 and G5. However, even if an employee is wearing a layer of flame-resistant clothing, there are circumstances under which flammable layers of clothing would be uncovered, and an electric arc could ignite them. For example, clothing ignition is possible if the employee is wearing flammable clothing under the flame-resistant clothing and the underlayer is uncovered because of an opening in the flame-resistant clothing. Thus, for purposes of Section 1926.960 G3, it is important for the employer to consider the possibility of clothing ignition even when an employee is wearing flame-resistant clothing with a suitable arc rating. Under Section 1926.960 G3, employees may not wear flammable clothing in conjunction with flame-resistant clothing if the flammable clothing poses an ignition hazard. 7 Although outer flame-resistant layers may not have openings that expose flammable inner layers, when an outer flame-resistant layer would be unable to resist break open. 8 The next, inner, layer must be flame-resistant if it could ignite. Non-flame-resistant clothing can ignite even when the heat energy from an electric arc is insufficient to ignite the clothing. For example, nearby flames can ignite an employee's clothing, and, even in the absence of flames, electric arcs pose ignition hazards beyond the hazard of ignition from incident energy under certain conditions. In addition to requiring flame-resistant clothing when the estimated incident energy exceeds 2.0 calories per square centimeter, Section 1926.960 G4 requires flame-resistant clothing when the employee is exposed to contact with energized circuit parts operating at more than 600 volts. Section 1926.960 G4I. An electric arc could ignite flammable material in the work area that, in turn, could ignite the employee's clothing. Section 1926.960 G4-2. And molten metal or electric arcs from faulted conductors in the work area could ignite the employee's clothing. Section 1926.960 G4-3. For example, grounding conductors can become a source of heat energy if they cannot carry fault current without failure. The employer must consider these possible sources of electric arcs. 9 In determining whether the employee's clothing could ignite under Section 1926.960 G4-3. 1. Flame-resistant clothing includes clothing that is inherently flame-resistant and clothing chemically treated with a flame retardant. See ASTM F1506-10A, Standard Performance Specification for Flame-Resistant Textile Materials for Wearing Apparel for Use by Electrical Workers Exposed to Momentary Electric Arc and Related Thermal Hazards, and ASTM F1891-12 Standard Specification for Arc and Flame-Resistant Rainwear. 2. The Occupational Safety and Health Administration used metric values to calculate the clearing times in Table 6 and Table 7. An employer may use English units to calculate clearing times instead, even though the results will differ slightly. 3. The Occupational Safety and Health Administration based this assumption, which is more conservative than the arc length specified in Table 5, on Table 410-2 of the 2012 NESC. 4. The dielectric strength of air is about 10 kV for every 25.4 mm, 1 inch. Thus, the employer can estimate the arc length in millimeters to be the phase-to-ground voltage in kilovolts multiplied by 2.54, or voltage, in kilovolts, times 2.54. 5. ASTM F1506-10A defines arc thermal performance value as the incident energy on a material or a multi-layer system of materials that results in a 50% probability that sufficient heat transfer through the tested specimen is predicted to cause the onset of a second-degree skin burn injury based on the Stoll, footnote, curve, Cal/CM2. The footnote to this definition reads, derived from Stoll, A.M., and Chianta, M.A., Method and Rating System for Evaluations of Thermal Protection, Aerospace Medicine, Volume 40, 1969, pages 1232 to 1238, and Stoll, A.M., and Chianta, M.A., Heat Transfer Through Fabrics as Related to Thermal Injury, Transactions, New York Academy of Sciences, Vol. 33, 7, November 1971, pages 649-670. 6. See Section 1926.960 G4I, G4-2, and G4-3 for conditions under which employees must wear flame-resistant clothing as the outer layer of clothing even when the incident heat energy does not exceed 2 calories per square centimeter. 7. Paragraph G3 of Section 1926.960 prohibits clothing that could ignite and continue to burn when exposed to the heat energy estimated under paragraph G2 of that section. 8. Break open occurs when a hole, tear, or crack develops in the exposed fabric such that the fabric no longer effectively blocks incident heat energy. 9. Static wires and pole grounds are examples of grounding conductors that might not be capable of carrying fault current without failure. Grounds that can carry the maximum available fault current are not a concern, and employers need not consider such grounds a possible electric arc source.